Hi everyone! Today we will finally look at the mysterious topic of equality in type theory. But before we do that, let's give ourselves something to play with. So let's introduce the lateral numbers. So this is in data.nat and you can look it up. It's imported from the built-in file and it's a data type which has two constructors, 0 and successor. Right, and we've done this before, but just to warm up a little bit, let's define addition on the natural numbers. So this is a typical definition by pattern matching. So the first thing we have to decide is if we are going to split on the first argument or the second argument. And in this case, there really is no right answer. Both work fine, and there's more a convention than anything else. So let's try to split on the first argument. So do Control-C, N, press enter, and I get two cases, it's 0 or a successor. Okay, and now we have to think and actually give something back that makes sense. There's many choices, but there's only one that really implements addition. Right. So what is 0 plus m? Well, that should probably be m itself. So let's give that. And what is suc n plus m? Well, we would like to do a recursive call because that's what we often do. So recursive call will be n plus m, right? But if I just return this now, then we would just keep peeling off sucks from the left-hand side until we get down to 0, and then we will return the second argument. So that would not be right. We need to have the same numerical value on both sides of the equality. So at the moment we have one more on this side, right? Because we have one more suck here. So we have to add one more here, and there's a few ways we could do it. We can't really add it to the end because then we would just say Brexit equals Brexit. It's not a very good definition. We could add it to the m, or we could add it, which is the typical way to do it, to the outside of all of this. Okay, so now we see that we are doing a recursive call, but it's on a smaller n. So this is eventually going to go down to 0, and then we just return the rest. So we can try this by doing Control-C, Control-N, and then let's see what 42 plus 5 is. So you see this down at the bottom of the screen. I enter the expression, and I press enter, and I get the answer that this is 47. That seems to be right. Okay, so now we have something that we can actually talk about the qualities of. And the way we do this is that we we open and import this particular module from the standard library. We could also define it ourselves, but this is a convenient way to do it. So let's see what's in here. I middle click on this. Okay, and I go further down in the hierarchy, and finally I find this agda.built-in equality module, and this is where equality is defined. We see that it's a data type, and it has exactly one constructor. And what else does it have? It has a parameter a and a parameter x which lives in a, and then if we give it any other a, we get a setback. And there's exactly one way to make an inhabitant of this type, and that's to give the same x as the second argument. So there's one constructor called refl for reflexivity, and it says that x is equal to itself. Right. So a priori you could feed in many things here, but the only one where you have a constructor actually targeting this type family is if both this x and the second argument is the same. So we're claiming that equality is given by reflexivity. Okay, so let's just go back to where we were, and let's see how we actually use that. So hopefully if that seemed a bit strange, it will become clear in a second. So let's say that we wanted to prove that 0 plus n equals n. And we wanted this for every n, so that's why we introduced this with one of these dependent function spaces, because that's how we represent it for all, remember. Okay, so how do we prove that 0 plus n equals n? Well, this is one of the defining equations here, right? So if I actually normalize this goal, then I say that what I have to prove is that n equals n, because 0 plus n has computed away and become just n. Right? So this is easy to prove. I just give refl. Okay, the file. But what about the other way around, if you want to prove that n plus 0 equals n? Well, you could think that this is just as easy, just give refl, what else could we do after all? But if I do that, then Agda complains that it's not obvious that n plus 0 equals n. And why is that? Well, there is no equation up here which explicitly says that n plus 0 equals n, right? So we can only give refl if it's obvious just by computing that the two sides are the same. But here, it is not obvious by computation. So what we have to do is we have to pattern match on the n to see what happens if this is more specific. So the slogan we're using is that we're asking ourselves, why is this thing stuck? And in this case, this thing is stuck because we don't know what this n is. Whereas up here where we define plus, we only make progress if we know what the first argument is. But here we don't know what the first argument is yet. So let's pattern match on the n and see what happens. Okay, so if n is 0, then what do we have to prove? Well, we have to prove that 0 equals 0. And that's because now, when n is 0, then this first line applies. And we get 0 plus 0, which computes down to 0. And we have to prove this simple thing. So that's refl. Right. Okay, and in this case, the second line applies, right? So now what we have to prove is that suc of n plus 0 equals suc of n. Because the suc of n is the n we're looking at, and we have computed according to this line, where we had suc of n plus 0, and that computes to this. Okay, so that looks like something we could do if only we could kind of peel off these sucs both on the outside, right? Because then, with a recursive call, I know that n plus 0 equals n, so I just need to feed that into the fact that if I apply suc to two things that are equal, then I still get something that's equal. And that's something that we can prove in general. So this is called cong in the standard library, but let's prove it ourselves because it's easy. So what does this say? It says that if you have any two sets a and b, and if you have any function f from a to b, and any two arguments that you know are equal, then f applied to x will also be equal to f applied to y. And how do we prove this? Well, this is what we have to prove. We have a proof p that x equals y, so let's pattern match on that p and see what it could possibly be. Okay, so I pattern match on p, and we see that there's only one case, refl. But now something magical has happened, because it only makes sense for refl to match here if x and y are actually the same thing. Because refl was something I constructed a proof of x equals x. So by pattern matching on the p, we have recovered more information about the rest of our arguments, namely that x must be equal to y, definitionally, which means that it's now much easier to prove that f of x equals f of y if they are definitionally the same. Right now we have to prove that f of x equals f of x, which we can do with refl. Right, so by pattern matching on this proof, we only had to consider a very specific instance. There's only one way we could have gotten in this situation where someone gave us a proof that x equals y, and that's the case if they were really equal to begin with. So that's a very useful thing that we're going to use all the time. We're going to move it up here so that we can use it in here, because now we see that if I say cong of suc and this thing, that should finish off the proof. So cong of suc says that if I just, well, let's make this a whole for now. Okay, so cong of suc, and now before we had to prove that suc of something equals suc of something, but now we just have that inner thing left, which we get away with by doing a recursive call. Okay, and then we're done. Let's do the same thing here. So the first thing we're doing is we're saying why is it stuck? And in this case it's stuck because we don't know what this n is on the left hand side of this plus. Right, so let's pattern match on the n. Okay, if it's 0, let's see what we have to prove. Well, we have to prove that suc m equals suc m. That's easy. And otherwise here we have to prove that suc something equals suc something. Well, let's hope that peeling that sack off with a cong is going to make some progress. And then we are left with this goal, but that looks a lot like the thing we are trying to prove overall, so that should be a recursive call to the smaller n, and that finishes that. Okay, so what have we learned? Well, we use refl to prove obvious things when we say that x equals x, and if it's not obvious yet, then we often ask ourselves, why is it stuck? So that we can follow the same pattern as in the definition of the function as in the proof about the function to make it reduce. And finally, we use congf to peel off an f from both sides in order to continue making progress on smaller things.